Jeremy?
No problem. I assume that my screen is visible.
Yes, all good.
Cool. Nice to see you guys. You probably all received some emails from me in the last couple of weeks, and I think I met quite a few of you at Amberley about a month ago. It's nice to be talking to you again. I just wanted to present something to you that can maybe extend your ability to use Fusion360. I've probably got a feeling that a lot of you have played around in Fusion while you've had access to the software and flicked through some of the menus to see what's available to you, but maybe you haven't had a chance to try FEA yet. So I'm just going to give you a 10-15 minute crash course on it, and we'll just skip through pretty quickly, and you can maybe use this as a tool today as you keep designing. So why would we use finite element analysis? Well, it's a pretty simple workflow loop. You will design your product in Fusion, you can test it in Fusion, and then based on the test results, you can iterate all within one software package. It's really pretty handy way to do things. So what is finite element analysis? Essentially, it's the breaking down of a model into a set of finite elements. In this case, it will be represented as a mesh that software can solve the propagation of forces through a part. It's essentially something that you could do by hand. You could do it analytically for very simple geometry. It's just not something you're practically going to do. Engineers don't do it. We rely on software. We're taught how to do it. Matt's probably taught me how to do it at some point. But it's a way to sort of speed up this design process, especially for complex geometries. So essentially, you take a part and you break it down into a set of elements and you solve for forces through that part. I'm not going to go into a lot of the engineering stuff, but just a very brief overview of a couple of terms that are probably going to come up a lot, and you'll probably want to understand what the software is spitting back out at you. But two important ones are stress and strain. You guys are probably all familiar with stress strain curves. I know a lot of you work with materials anyway, so you're probably very familiar with how this stuff works, but stress is just a force over an area. In SI units, that's newtons, and it's represented in pascals. Strain is just the change in length, for instance, for this example here, a uniaxially loaded rod. So it's just the change in length over the original length. That's a dimensionless unit. It's just a representation of what's occurred as a stress has been passed through a cross-sectional area. So what can FEA spit back out at us? If we set up a simulation and input all our boundary conditions, we can get an idea of the stress in the part, the strain in the part, maybe its displacement, how far it's going to deflect. That could be an important consideration, and maybe even a factor of safety. Now, when you start doing this investigation, you'll probably come to the realization pretty quickly that stress and strain are not material properties. It doesn't really matter what material you pick. They're purely based on geometry. Matt's laughing for some reason.
No, 100% agree. We spend so much time making sure your material's right to make it stiff enough, and you could just thicken it and it'll be way stiffer than any material choice. So it's just, yeah, it's good fun.
Yeah. So things like displacement and factor of safety, they are dependent on the properties of the material, properties like toughness, strength, yield strength, Young's modulus, stuff that we probably won't go into now because it maybe starts to get a bit complicated. But you can pick any material in Fusion and quickly get an idea of the kind of stresses that will be going through it. Then you can do your own research on what kind of material properties your print material, maybe PLA, has, for instance, and you can make some decisions based on that. There are options to pick particular materials in Fusion, but my guess would be, as Fusion might not know exactly how everything's layered or what kind of infill you're using, you might not get very accurate results. So that's just a consideration for you. Some of the limitations of FEA, you should try to think of FEA as a design tool, not an infallible solution. You're certainly not going to get research level accurate results from Fusion360's implementation. It's not physical. Very few FEA solvers are. But you could use improved FEA solvers like maybe the ANSYS Workbench or Abacus if you really care to get as accurate a result as you're going to get from software. But that's neither here nor there. So how would we set up an FEA system? Very simple flowchart. Just create your geometry in Fusion. Position everything the way that you want it to be when you're testing it. You can use joints to help you position everything correctly. We've probably gone through before. You're probably quite familiar with how joints work. Choose a material, like I just mentioned. It's not always important. For this example, I'm just going to use steel because it's very common. It's easy to get material properties for steel. Set your boundary conditions. Boundary conditions are things like constraints, forces, loads, everything that's sort of constraining or putting boundaries on how this solution will be solved. You can set contacts between the bodies. So I'll show you shortly in this small example that I've got how that works. Then you mesh the geometry. Meshing is that discretization of the geometry into small finite elements. And that's pretty much all you have to do. Then the system will solve it for you and you can inspect those results and iterate based on what you found. So let's just have a look at a really simple practice scenario of a really, really stuck bolt. So something that maybe requires about 180 Newton meters of torque to unscrew. Maybe it's rusted, or maybe someone just used a whole bottle of Loctite on it or something like that. So there's a lot of, here's something I prepared earlier in this because a lot of things take a little while to load and to solve. So we'll just sort of step through the quick setup. So I think I might have spoken to a few of you in the past, but if you weren't aware, there's an option in Fusion to just bring in parts from McMaster Car, standard bolts, nuts, threads, that sort of thing. That's what I've done here. So I've sort of, we'll go back and we'll just do it sort of step at a time. Import a nut, reposition it. We're going to use that as our base, so we'll fix that at the end. Then we'll sort of bring in a bolt, a threaded bolt. We'll position that in a way that makes sense, and we'll create a sketch of a spanner, for instance. I know some of you worked on spanners in one of the previous workshops with Matt, and I thought that that's a pretty simple scenario that probably a lot of you are, familiar with. Create a sketch, maybe create it in a way that's mirrored or something, so that if you need to, you can just drag the design around, but we won't do that for now. Then we can, let's just get out of that. We can extrude our sketch. So we've got a very basic shape, and then we can position it. Now, one thing that I'm going to note before we move on to solving this simulation, I assume that most of you guys can get up to this part pretty easily. When it comes to applying forces in Fusion or any FEA software for that matter, usually it's going to ask you where you want to apply a load. Now, sometimes you can apply that load at a vertex, as in just a single point, but that's not going to be very realistic. Usually you're going to want to apply it to a face. By default with this design, this would be the face that I have available to me. That might not be realistic. This is about 120 millimeters long. I doubt anyone's hand's quite that wide. So if we wanted to set up a certain scenario, maybe we could split the face just to create a small area that we can apply a load to. That's something useful that you should keep in mind. You can just draw a sketch and split the face so that you end up with two separate faces. So let's move into setting up our FEA. So you can see there that we've got two separate faces. So this little drop-down menu up the top left, you've got all your options here. You go into simulation and it will give you an option. I've sort of skipped through that part, but you'll probably be picking something like static structural. And then it's really just a matter of working through the top bar sort of systematically from left to right. So you can pick materials. There's a whole set of materials that are available, but I've just chosen steel for each of these. You could go through and change them if you cared to, but I think considering what I explained about material properties, it's not that important to start with. What is important is setting up your constraints. So constraining the model is really where your boundary conditions come in. So if we set this one up kind of simply, maybe we can say let's add some constraints here. Let's say that this face and this face are both fixed. So these are fixed constraints, and that's essentially setting this nut kind of as the surface that this bolt is threaded through, sort of locked in here. This nut is not going to move anywhere now. That's sort of our reference point. You always need to have a reference point for these things to solve. If there isn't at least one fixed position, you're not going to get any results. Then we can move on and add some loads. So for instance, let's put a load on this surface here. Now I said 180 Newton meters, and this is about 120 mil long, so that'll be about 1500 newtons. Can add a force. Now we've got a force, we're fixed. The only other thing that we really need to do now is add some contacts between these parts. So luckily Fusion can do this automatically. You can set a tolerance.
Jeremy,
So
I'm just going to interrupt a little bit
Sure.
there because I had this issue when I started trying to do FEA. I see when you've added a little load there, there's 2 faces on that side of the spanner.
Mm-hmm.
And that's very important. Sometimes it can be hard to select where you put the load. If you've got a very curved surface or lots of faces, it will try and apply it to that whole surface. So have you split the face there, Jeremy? How have you ended up having an extra little? Yeah. So you've split the face. So if you have that issue, when you're trying to apply, if you end up doing FEA on your designs, everyone, have a Google or send a little chat in the signal if you need to split a face, and we can guide you through that, because that'll bring you undone, like it brought me undone for many hours one day.
Yeah, as I mentioned, that was this sketch line here. So I just created a little sketch line on this face and then used the split function. So it's create, I think it's create or no modify, sorry. And there's a split face option right here. So you can choose the face and then choose the tool, which would just be the line that you drew, and that will split the face in two. So that's what I did, Matt. So back into our simulation, we have our load applied, and then we can use the automatic contact. So this essentially just lets you set a tolerance for the gaps between faces. So if we keep it at 0.1 of a mil, it's going to capture everything here because we've sort of designed it in a way that that everything's flush anyway. So that should be fine. So we'll click that to generate. Now, I'm going to ask you guys to maybe pull out your signal, and just based on intuition alone, given what I've told you, we've got one force applied here, this nut is fixed, and then there'll just be rigid contacts between each of these parts. So you're going to imagine that this thread is locked pretty tight into this nut, and this spanner is firmly affixed to the top of this head. It's not going anywhere. You could imagine that it's glued to the top of the head or welded or something like that. Where might you expect, based on your intuition, that you might see the greatest stress in this system? If you could just throw out a couple of ideas, maybe you're thinking in the handle, maybe at the neck of the spanner, maybe in the head, maybe in the thread, maybe at the nut.
Scott says on his wrist. Good on you, Scott.
Not modeling that one.
Head and base of neck, my wrist, sheared through the thread, head of the spanner, neck of the spanner. Yep, I think you guys, jaws, neck, face of bolt, spanner head. All right, so in the spirit of, here's one I prepared earlier, the next step would be just to click solve here. You don't actually have to mesh it if you don't want to. It will do it for you all in the solve step, but I will circle back to that. You can control the mesh if you want to, but you needn't. Once you have all these, your constraints, your loads and contacts set up, all you need to do is solve the problem. So let's skip ahead to something that I solved earlier. So what I'm displaying right now is contact pressure, but let's have a look at stress and let's animate it. And what we'll do is we'll set the deformation to be exaggerated. So this is going to show not the actual deformation, but approximately 5 times as much, just so it's a bit easy to visualize. And let's see what actually happened based on these loads. So if we click play, we can see that, well, the bolt is twisting here. The spanner seems perfectly fine, but we're starting to get, let's show the min and max. So who was it that guessed thread? Carlton, someone up the top, sheared through the thread. Brad got it. Nick. So there were a few people that sort of had the right idea here, that with the constraints that we set, the max stress point was right there in the thread. So we learned something, but we didn't exactly learn much about designing this spanner. So let's instead fix the top of this the top of this bolt as well, and we can have a look at how the spanner performs. So once we've fixed that bolt, so what I've done is I've just added a fix to the underside of this bolt here. And I should just note quickly that setting these constraints is going to have a big impact on the accuracy of your simulation. This is something that everyone who does FEA struggles with, is correctly setting boundary conditions. It's nearly impossible to get something that's going to be one-to-one accurate with what you see in real life. And I know that through my undergrad, there were plenty of marks deducted for, poor boundary condition settings. And this is just something that you're going to have to play with the software a lot to sort of get the right feel on how this works. And this is far from perfect, but it's just an example. So let's have a look again at what happens when we've fixed this this bolt. So now we can see that. Let's set it to stress so we can see the stress. So now we're starting to get a lot more stress through the spanner itself, and we're starting to get areas where the stress is concentrating, especially around these sharp edges. So if I sort of wait for this to animate, I'll spin it around and we'll have a look. Let's just say stop the animation. Right, so these areas here are the areas of interest or worry. So maybe if I was designing this spanner, I might think, well, okay, let's have a look at exactly what's going on here. So we can create a surface probe, and we can sort of have a look at what kind of stresses we're seeing in this part. So it's represented in megapascals. You might remember a couple of minutes ago I told you that stress is usually represented in pascals. You can see what's happening here. Now if I just quickly jump back into a PowerPoint real quick, one last slide I'll show you. Let's swap the screen across. So this is a stress strain curve, something that engineers use all the time. I'm sure you're familiar with it. For steel, we have an ultimate tensile strength of about 420 MPa, typical mild steel, and a yield strength of about 250 MPa. Now this yield point is the point where you've gone beyond the elastic properties of the steel and you're going to start getting permanent deformation. So if I was designing something, I'd probably want to keep it in this elastic region here where any stress that you put through the part, it will still bounce back to its original shape. So you can consider maybe 250 MPa as our absolute upper limit for something that we want to see in our part. Obviously, if we were designing for a factor of safety, we'd go beyond that. If it was a factor of safety of 2, maybe we'd want 125 MPa as our max for this part. That really depends on what you're designing for. It might not be relevant for what you're designing this week, but maybe we can make some changes to the geometry to see if we can get that stress down. So what if we put in maybe a couple of fillets or curves in here? Does that make much of a difference for the same geometry? Let's have a look. Yeah, it's come down a little bit, 350 down to somewhere in the region of about 310. That's good. And what if we were to maybe beef it up a little bit more? I know that we're starting to run a little bit long here, but now this I wanted to point
Jeremy?
out. Yep, sure.
Brendan here at Cuttable. Due to bandwidth, your speaking is about 30 seconds in front of our screen. So can we just
my apologies.
Make small talk for another 10 seconds, and then the screen probably will have caught up, and I can see the fillets just coming up now.
Okay, really interesting.
Yeah, I don't know, not sure why that's happening, but anyway, we're probably about there now. Carry on.
Sure.
We can turn let's turn our videos off, Clara, Bill,
Yeah.
and that'll just maybe help Cuttable a bit too.
Right, so I'll try not to rush through. I'm just keeping in mind how much time we've got, but adding some fillets definitely reduces the stress in these areas, but we're still not really where we want to be. We're still sitting around 300 MPa, which is below the ultimate strength of steel, but maybe a little bit beyond its yield point. So if we were to apply this force, we might have some permanent deformation in this spanner, and that's probably something we want to avoid. So moving on, maybe we can beef it up a little bit. We've sort of thickened the width here. We've increased the radius of these fillets, and now we're looking at values in the 190 zone, which is below the yield point for steel. And we might still be pushing it a little bit more than we want to. Now, I just wanted to quickly point out that because of the way we've set this up, and this is a limitation you're going to bump into a lot, we've fixed this nut. So actually, the highest point of stress we're getting is right here at this contact point. And that's a limitation of the boundary conditions we've set. So you have to keep in mind, you need to be able to filter with your brain the results that you're getting and not just look at this and say, right, the max pressure there is 485 MPa. That might not be the case for the important part. This is a result of these cells here being highly compressed based on the fixed geometry that we've set for the top of the nut, for the top of the bolt. Right, now we can talk just very briefly about meshing. You can always check the mesh visibility up here. So I've had it turned off for the most part, but you can turn it on. Now the only difference between this and the last model is just the mesh density. So you can see here, this is what it did by default. I've just increased the density a little bit here. And as I do so, I get kind of smoother gradients and maybe slightly more accurate results. It's not guaranteed, but you can play around with that. I think that's all I'll say about FEA. I'll certainly be around all day if you guys want help doing any of this. There's so many different ways you can apply it, but I would just spend a little bit of time going through this top toolbar. The one other thing that I wanted to quickly touch on is there is also the option for generative design. So if you were to take this exact same part, and it does take a little bit of setup, I'm not going to go through it all, but you can probably fumble your way through it. And we can ask Fusion to come up with some designs for us. Say we wanted this to instead be made out of aluminium, for instance, and we wanted to reduce the weight as much as possible. You could ask Fusion to do that. It's going to create some really funky looking stuff, but it will start to cut away material where it isn't needed based on the particular load case that you have. And here's what Fusion thinks that spanner should look like if it was made out of aluminium, and if we wanted only the minimum material needed to fulfill that task of applying a given force. That's the kind of thing you can do with generative design, but that's a whole other thing on its own. If you get time, maybe have a go with it while something's printing, but I wouldn't worry about that too much for now. I would recommend that you use FEA as just a brief design tool though, and it's something you could throw into your presentations tomorrow and say that's something you considered. But yeah, if you've got any questions, you can sort of ask them now, or I'll be available through the Signal chat all day. I can jump into one-on-one calls if they're required.